Talking about normal field extensions. So the definition was that if we have an algebraic extension okay. No. But the line still is valid, no? So something like that. An algebraic extension L over K is called normal. If every irreducible polynomial which has a zero in R splits already over L into linear factors. Okay, so this was the definition, and then I had said that we had this result that says there's a kind of, in some sense, simpler way of seeing it. An extension is normal if the bigger field is the splitting field of a polynomial with coefficient in the smaller. So finite extension. L over K is normal if and only L is a splitting field of a polynomial. Small f and coefficients in the small. Okay, so we had proven the difficult direction. So this was done using this result about extensions of field isomorphisms to splitting fields, and now we want to show also the other direction, which is easier. So assume we have a finite normal extension. So we can write, as it's a finite extension, it's a finite algebraic extension, so we can write L equal to K A1 to AN. So it's for some elements. Now we know that finite extensions are finitely generated algebraic extensions, so by adding finitely many algebraic elements. So let Fi be the minimal polynomial of Ai over K. And as L over K is normal, this Fi splits into linear factors. So thus also F, which I define to be the product of the FIs, splits into linear factors. Over L. So we see that F splits, and now the claim is that L is a splitting field of F. So clearly, by definition, L splits, F splits over L. And if any intermediate, and if I have an intermediate field over F splits, over which F splits, it has to contain these A1 to AN because they are the roots, because they are roots of F. So, and if F splits over an intermediate field, F, then A1 to AN are elements of F. So thus A1 to AN, which is equal to L.
Why?
What?
How we are sure that all the AIs are roots of the minimal polynomial of AI?
No. So we have. So
I mean, we picked one, and
no,
and Fi is a minimal polynomial of a specific AI.
yeah, and then I take F to be the product of all of them. So we take.
Yes, okay.
Yeah.
Okay.
So
Yeah.
I have that. I take the I take all the minimum polynomials and they split. So that's obviously F splits over L, and it does not split over any intermediate field except for the whole of L. And so L is the splitting. So okay. So now let's see, where's my page? So this is as much as I wanted to say for the moment about normal extensions. We will obviously come back to it. So basically, and most of the time, the point is that to find, to see that an extension is normal, we maybe construct it as a splitting field of some polynomial. But then, when we want to use it, to prove some theorems, we usually want to use the other result, that any polynomial which is irreducible and has a zero in the splitting in this bigger field, then it has to split. So therefore, it's good to have these two different.
Is this theorem says that if it happens that one polynomial can be split, then we're sure that the finite extension is normal. Every other. This is the meaning of this theorem. That if it happens, we have one polynomial that is split over L, and L is finite extension, that is normal.
No, it's not when it has to be the splitting field. So the statement is, so normal means that any polynomial in the smaller field which has a 0 in any irreducible polynomial with coefficients in the smaller field, which has a 0 in the bigger field, already splits. Okay, that is the definition. Now this statement says, if I, so we are only interested in finite extensions, so let us assume we are dealing with finite extensions. So if we have a finite extension, then it's normal if and only if the bigger field is a splitting field of
A polynomial, like one polynomial.
of one polynomial. And so that means, so in particular that means that if you have, if you look at the splitting field of one polynomial and you take any other polynomial with coefficients in the smaller field, which has a 0 in the splitting field, then it splits into linear factors. That's part of the result we proved. Yeah, but it's okay. So now we want to talk about separable extension. I told you that the Galois extension is one which is normal and separable, and so we come to the second property. Is it separate? I think so. Extension. So separable extensions are about multiple roots. So, or rather that there aren't. So if f MTH is a polynomial, so it will split somewhere. So that we can write f equal to b times x minus a1 times x minus an over some, so splitting into linear factors over some extension field. Extension L of P. Now it could happen that some of these AIs are equal, so that we have a higher power. So if some AI goes inside, so for instance we have A1 is equal to A2. So that means this whole thing is divided by x minus a1 squared. And we say that a1 is a multiple of f in F. And now somehow these multiple roots cause some trouble later, and so we want a criterion which means that in certain situations our polynomials won't have multiple roots, and so for this we introduce the notion of separable extension. Okay. So let's do this properly. Maybe I first write this more precisely, definition. So I take that f the polynomial kx, and let f equal to b times x minus a1 to the m1 times x minus an mn. I'm going to write this L. We are splitting of f over an extension L of k. And we assume with where m1, so where these mi are all bigger than 0, and the AI are distinct. So assume we are in this situation, we have somehow put together the factors which are the same. So then we say so if mi is bigger than 1, or it's maybe first if mi is equal to 1, we say AI is a simple root. Of that, and obviously if mi is bigger than 1, we say that AI is a multiple root. Of multiplicity mi. And now, with this, once we know the story of the multiplicity, I can define what it means for an extension to be separable. An algebraic field extension L over K is called separable if the following holds. If it starts very similar to normal, so if any irreducible polynomial with coefficients in the smaller field which has a 0 in the bigger field, has no multiple roots anywhere, so it has no multiple roots in its splitting field. So this is, again, a slightly complicated definition. So it's the same kind of story as for normal. We take an irreducible polynomial with coefficients in the smaller field, which has a 0 in the bigger field, and we ask something for all such polynomials. In this case, we ask that it has no multiple roots. I mean, no multiple roots anywhere, which is the same as saying it has no multiple roots in its splitting field. Now, in the same way as it is for normal, an irreducible polynomial which has a 0 in the bigger field, up to multiplying by a constant, is just the minimal polynomial of its 0, of the thing that it has a 0 of. No? If you have an irreducible polynomial with this, so the minimal polynomial is the unique monic polynomial which is irreducible in Kx, which has a certain given element of L as its 0. And so that means if I have such a thing, it's up to multiplying by a constant, which is irrelevant, just a minimal polynomial. So we can also equivalently say, that's maybe easier to remember. So L over K is separable if the minimal polynomial of any element A in L has no multiple roots in its splitting field. So this is this condition. Now, as this is all about, and so this somehow, when one wants to study field extension, it's very often in terms of minimal polynomials, and then these will not have multiple roots, and that will be useful. If we make the condition that it's separable. So now we need we have to understand when a field extension is separable. We actually will find out that in characteristic 0, all field extensions are separable, so this condition is somehow always true, unless some extreme cases. But we need to find that out. So we have to find out how to check whether a field extension is separable. And as this is about multiple roots, we have to find out what is the condition for polynomials that have multiple roots. And obviously you know this, some kind of criterion for that already, because as you know from analysis, you have a multiple 0 of a polynomial is a point where both the polynomial and its derivative vanish. And this will also hold here, if you just formally define the derivative. Here we do not do analysis, so derivative is just something one writes down by the usual formula. So this is not here. So, for definition. So let f be a polynomial. Some I 0 n a I x to the I, polynomial with coefficients k. So then the derivative of f is just given by the usual formula. F prime is equal to sum I equals 1 to n ai. We want it I times ai times x to the I minus 1. So we just define it by the formula that one derives in analysis. And it's easy to check that the derivative is in a suitable sense linear. So if you take the sum of two polynomials or multiply by constants, it will be linear, and you have the Leibniz rule for products. This is an exercise, so easy to check. So for A, B, in K and F, G in Kx, we have first that AF plus BG. If we take the derivative of that, that's A derivative of F plus B times the derivative of G. So that means derivative is linear, and the second statement is that we have the Leibniz rule. If we take F times G, derivative of this is F times G prime plus F prime times G. Okay, and if you just obviously this is something one learns also in analysis, and then one proves this formula, and so in general, and one proves this formula for polynomials. But here, obviously, if one just takes this formula, you can just put it in and check, and it's true. And so now we can see the statement I just said. So if I take a polynomial, maybe, I don't know, so it's not constant, and let, I think we would also L over K be a splitting field. Of F. So then, and A and L, then A is a multiple root of F, if and only F of A is equal to 0 and F prime of A is equal to 0. Okay. Obviously this is quite simple. You just have to write down what it means. So let R be the multiplicity. So this will prove the multiplicity of A as a root of F. Then it means we can write F as x minus A to the R times G, with G in X, and G of A is not 0. Now I can compute F prime at A. First I compute F prime. Now it's easy to see from this, if I take x minus a to the r, this gives r times x to the x minus a to the r minus 1. I mean, you can easily deduce this from this, and obviously you also know it anyway. Or we can take the derivative here by the Leibniz rule, so x minus a to the r times g prime. So you can see that this here is a 0 of order precisely r minus 1 at A, because it's divisible by x minus a to the r minus 1, but by no higher, but this does not have A, if A is a 0, and this has a 0 of order bigger or equal to r. So therefore the whole thing is divisible by x minus a. Anyway, certainly the whole thing is divisible by x minus a to the r minus 1, but not to 1 power more. So this has a 0. So we see that the 0 of the derivative is always, so if we have a 0, the 0 of the derivative is 1 less precisely than the order of the 0 of f, and so the claim follows. A is a multiple. So this is obviously one with r is bigger equal to 2, which is if f prime of A is equal to 0.
And f of A is equal to 0?
What?
And f of A is equal to 0?
Yeah, but here I had assumed, okay. I had implicitly assumed that was 0, but okay. So I meant if A is a 0. But okay, you can also write that. Okay. So now that's kind of trivial. Next thing is slightly more surprising, namely, if I assume that f was irreducible to begin with over k, and A is a 0 in the splitting field, then it will follow that the derivative of f must not just have a 0 at A, but the derivative must vanish completely, must be the constant polynomial 0. Let's see. So this is, I call it theorem, although it's quite easy. Let f in Kx be irreducible. And f has a multiple root in its splitting field if and only if f prime is the 0 polynomial. Okay? It's a rather big step to begin with, from the fact that it must also vanish at the root. It now must vanish, must be just 0. But obviously that comes from the fact that we have assumed it to be irreducible. Ah, yeah. Forgot to say that, and then we can come back to it. So, proof. So let L over K be the splitting field of F. So obviously, if f prime is equal to 0, then every root A of f in L is a multiple root. Because we had said it's a multiple root if and only. And so therefore, we find that if f prime is 0, then it has multiple roots. Okay, but now conversely, the non-trivial direction, assume, so let A in L be a multiple root. Then what we have just seen, f of A is equal to f prime of A is equal to 0. But no, f is irreducible, so up to multiplying by a constant in k, it's just the minimum polynomial of A. So obviously the whole question is not changed by multiplying f by a non-zero constant, so we can assume that f is monic. So we can assume f is the minimum polynomial of A over K. So That means it's a monic irreducible polynomial which vanishes at A, but we also know it means that it generates the idea of all polynomials which vanish in A. So as f prime of A is equal to 0, it follows, therefore, we have that f prime is an element in the idea generated by f. No, because f generates negative all of those. So that means prime is equal to g times f, g in Lx in kx. But obviously, so it follows. So thus, if g is different from 0, then it follows from this the degree is additive. So the degree of, and it follows that the degree of f prime is equal to the degree of g plus the degree of f, which is bigger equal to the degree of f. But this is a contradiction, because by definition, you just have some aix to the I is sent to some I times aixi to the minus 1. So we see that the degree of f prime is at most one smaller. But by definition, degree f prime is smaller or equal to the degree of f minus 1. No? Now, and so, therefore it follows that g is equal to 0, and therefore f prime is equal to 0. Now, okay.
But if f prime is equal to 0, does that mean f is constant?
Well, that's an interesting question. That was the next question I wanted to ask you now. What do you think? Does it mean that?
No. It depends.
Yeah, because obviously you learned in analysis that this precisely means that f prime is constant, but we are not doing analysis here, so
And p characteristic.
yeah. So if the characteristic is p, it can happen that but anyway, so maybe I can first use what you said to make the main. What is it? So first, obviously, this analysis argument works in characteristic P, so it follows the corollary. If the characteristic of K is 0, then L over K is separable for any algebraic extension L over K. In fact, and this is just because by definition, if f is not constant, so we have somehow a leading term a n x to the n, so some I f some I n a I x I, where a n is different from 0, then it follows that f prime is equal to some I to 0 and 1 to n minus 1, AI times I times x to the I minus 1, where the leading term n times an is also non-zero. And so it follows f prime is non-zero. But obviously, so what one needs here that this is cannot be zero. So so actually there is a word for this kind of thing, definition. A field K is called perfect if any algebraic extension L over K is separable. So we see, so thus every field of characteristic 0 is perfect. Okay, so let's see what can happen in characteristic P. Yeah?
If f dash of A is 0,
What?
f dash of A is 0, then f dash is in the ideal of GL by f.
Yeah.
Why can we see this immediately?
Well, this is, it's just what we had proven earlier that so f is the minimal polynomial of A. And we know that the minimal polynomial generates the ideal of all polynomials which vanish at A. Now f prime is one of them, and so therefore it must be multiple of f. Okay. So that was one of the results to prove. Okay, so just as an example, so for instance, if so for instance in characteristic P we have, if I take for instance, if we just take x to the p and I take its derivative, this is equal to p times x to the p minus 1, but p is 0. So you can see you do have some constant polynomials which vanish. So more precisely one can easily show, if one wants, it's an exercise. So let K be a field of characteristic P and F in Kx, then f prime is equal to 0 if and only if f is a polynomial which depends only on x to the p. So I could say it like this, that there exists a polynomial g in Kx with f of x is equal to g of x to the p. No? Because clearly one direction is here. If it only depends on x to the p, if we take the derivative, everything vanishes, and you can also check the other way. I should however say that we are not going to prove it, but one can prove that also every finite field is perfect. So every finite, every algebraic extension of a finite field also is separable. But that's more difficult to see, but it's also true. But there are fields which are not perfect, which are somehow some, infinite fields of characteristic P. I don't know, in Mood I don't know explicitly an example, but there are examples. There are many examples where of non-separable field extensions, but this is not for finite fields, but for big fields and characteristics. Maybe, I don't know, maybe just, I don't know, I haven't checked it. So. Okay, I know, this one is.
So could you give an example of irreducible polynomial on some field such that it has multiple roots?
Yeah, this exists, yeah. In characteristic P, but only over infinite fields of characteristic P. I don't know, but I haven't thought of an example, so I would have to look it up. I mean, maybe just, it could be something like you take the field of rational functions with coefficients in a finite field, or something like that.
Question field?
What?
Question field?
Yeah, the quotient field of the polynomials with the finite field. You could try with that, but I haven't checked it whether it's true. But I think that most likely would be an example. Yeah. Now we come to, so we want to see how useful this separable, this condition of separable is. So we have studied, at the beginning of this chapter on fields, I introduced simple algebraic extension. I said they are kind of simple, I mean easy to describe and easy to understand. And as they are so simple, we would really like that all field extensions are like that. And so this actually turns out to be true if we only look at separable extensions. So if finite separable field extension will always be a simple algebraic extension, just given by adding one element. And so then we can understand in terms of what we have understood before. And so, in particular, if you're in characteristic 0, any finite field extension is separable. So we can add many elements to the original field, but then we somehow will be able to find one element which extends the whole, which gives us the whole field extension. And this is the theorem of the primitive element. Okay, which we will use as an important tool. So the statement is, so let L over K be a finite separable field extension then there exists an element A in L such that this field L is just given by adding this one element. Okay. Now, as you can imagine, so this is quite surprising, and will also obviously be a very powerful tool, because we can understand how, at least in the separable case, the field extension is much better, because we know explicitly what this is. So therefore, the proof cannot be too easy. So you will see that it's a bit tricky. And you also have to see, no, it's not clear what this has to do with this condition of separable or whatever, how this would go into the picture. I mean, it's completely unclear. So I will cheat a little bit. For simplicity, I assume that K is infinite. So if the characteristic is 0, it's automatically infinite because it contains the rational numbers. But I have told you that also finite extensions of finite field extensions of finite fields will always be separable, and this I want to exclude. So for simplicity, ACT, we assume that K is infinite. So a modification of the proof will work for finite fields. But I thought I could slightly make it simpler. So this is leads to some simplification to make this assumption. So we know we have assumed we have a finite field extension. So as L over K is a finite field extension, we can write L equal K A1 to AN for some elements AI in L. We know that the finite extensions are precisely the finitely generated algebraic extension. So it's, the finite extension is always given by adding finitely many algebraic elements. And so we have that. Now you have here n generators. We want to finally have only one. So we will try to do this by induction. So we make induction on n. So if n is bigger than 2, so by induction, we have that k, a1 to an minus 1, will be equal to ka for some a in n. So if we can make induction, so we have to. So then, if n is at least 2, the induction step just works. We can just do this, and so thus n is equal to k a n a. Or a n. So that is, by induction, we can assume that our original n is equal to 2. No? We just, if there are more than 2, we can apply induction to make it less. And obviously, so that means, in other words, if we can show it for 2 elements, then we can show it for any number of elements. It's also kind of clear. So therefore, we work with this. So therefore we can assume this, and I write L equal to K A B with A and B to elements in L. And we have to show that, so we have now kind of used this thing to reduce it, so we have reduced it to this. We have to somehow show that if L is given by adding 2 elements, we can instead just add 1. And we actually, I will show something stronger. L can be written as Kc, where C is obtained as a linear combination of these two, a linear combination with coefficients in K. For C is suitable linear combination C, right here, C equal to A plus Z times B, where Z is an element in K. Okay, I can just, so I want to find A plus some element in K times B, such that this is this. And in fact, what we actually find is that, so it's for a general linear combination, for all but finitely many such linear combinations, this actually will do it. So almost, if you take something at random, this will almost always be good. So let's see. So now we have to prove that. And this is not so trivial. So we take let f be the minimal polynomial of A over K. And so I first have to somehow tell you what I can choose as Z. I told you almost everything is good, but I have to tell you what is not good. So, and let G be the minimal polynomial of B over K. And I take F, the field extension of our L, such that both of these polynomials split into linear factors. And G split into linear factors. Okay. So let's look at the roots of this polynomial, or these linear factors. So, so that means we can write f equal to x minus x1 times x minus xn, g equal to x minus y1 times x minus yn. See? So it splits into linear factors like that. As it was the minimal polynomial is monic, so it just splits like that. So this is this. And obviously we know that A is one of the roots of this, and B is one of the roots of this. So I choose x1 to be equal to A and y1 equal to B. So I have x1 to xn and in f, and x1 equal to A. Okay, so this is the situation. Now we want to use that we have a separable field extension. So our polynomial G was irreducible as a polynomial in K, and we have that f over K, L over K is a separable extension such that G has a 0 over it, so it has no multiple roots in its splitting field. So that means all these yi are different. L over K separable, and G reducible over K. With the 0A, we have B, we have B is different from Yj for J from 2 to M. Now assume we want to, so let's solve. So we want to find now, say, an element, so for all I from 1 to n and j from 2 to m, if you want to find a Zij in K, not in K, in F, such that A plus B Zij is equal to xi plus yj Cij. So if you want to find this is very simple, because we can just, we have a linear equation, we can solve it. So this just means, so we bring this on the other side. So we have, what is it? B minus yj Zij is equal to xi minus a. So it means that Zij is equal to xi minus a by b minus yj. So this is the unique solution of this equation. Okay. So the only Zij which satisfy this is this. No, just this is element here. So this is a power element in F, but no, it could happen to be in K, but we don't care. Now we use this thing that is infinite, as K is infinite. There exists an element Z in K, which is different from all the Cij. So different from all Zij. So with suppose that I goes from 1 to n, j goes from 2 to n. So the infinitely many elements in K, we only have to exclude these finitely many elements. These are whatever, more or less n times m. And for all we know, they might not even be in K, but if they are in K, we have only to exclude these finitely many ones. And then this equation will not hold. We take any such C. So then, obviously, A plus dB is different from xi plus y yj z for all I equals 1 to n, j equals 2 to n. And so this is the thing that we take as our z. So our element we want to add is a plus z b. So you put C equal to A plus Z times B, and we claim that Kc is equal to Ka. Okay, clearly Kc is contained in KAB because it's just a linear combination. If the field contains A and B, it contains any linear combination, certainly. So now we have to show the other inclusion. Basically, we will have to show that A is contained in this. Then it will also follow from this equation that also B is contained. Or maybe, I don't know, or maybe show that B is, I think we have to show that B is there. Anyway, it doesn't matter. We have to show that one of them is there, then also the other one will be there. So, now until now we have just defined this stupid C, and we have made this rather unlikely claim that this is the case. Now we actually will have to eventually prove it. So, we define a polynomial. So maybe I should say, well, so we define a polynomial H with coefficients in Kc by we put H of x to be our original f. Now, maybe you remember that f was a minimal polynomial of A. And G was a minimal polynomial of T. So we define this as f of C minus Z times X. Okay, we just replace X by this. Now this will be a polynomial in Kc because we have this this element C, is in here, and Z just was an element in K, so this doesn't do anything, so it will certainly be here. So what we want to show is that this has a certain common divisor with G, and it actually this somehow will allow us to show that B lies in Kc. So let's first see what is H of B. Just compute H of B. Somehow the trick is done in such a way that H of B will be equal to 0. So this is f of C minus ZB. No, by definition. And C minus ZB is equal to A. So this is 0. Okay, so thus X minus B divides H. Where are we here? So B, this was so was in L, but maybe, but we also have this, in, say in. No? So B was a 0. Okay. Okay. So L was KE. But we can also obviously we can take it here, but we could also take a bigger field. We can take this f of x, which is the field where both f and g split into linear factors, which was an extension. So we maybe take this one. So B is also a zero of G in fx with G, thus x minus B is a common divisor of these two, of H and G in fx. Now, I want to show that x minus b is the greatest common divisor of that. If I know that, we have this thing that if something is the greatest common divisor and it's monic, then it is equal to, then it will be equal to the greatest common divisor as computed by the Euclidean algorithm, and so it means its coefficients do not lie in a field which is bigger than the field in which the original polynomials were. Now, we had this result. I told you then that this would come in a surprising way. And so, anyway, we'll come to that in a moment, but because of this, I want to show that this is the greatest common divisor. Maybe I can already conclude here. So assume this is the case. So assume we have shown this. So we show from the Euclidean algorithm so if f and g are in kx and L, so now I need whatever. L over K is a field extension. In our case, it's F over K is a field extension. And L in f of x is the greatest common divisor of f and g in fx, which is monic. Then L is an element in Kx. So this was the result that we had. So therefore, if we assume this now, that we have already shown that this is the greatest common divisor, then it follows that x minus b is an element in Kc of x, because we had that H was in Kc of x, and G was in Kx. Okay, so both of them are in Kc of x. Okay, so obviously this implies B is an element in Kc, and thus A equal to what is it? C minus Cb is also in Kc. Thus Ke is contained in Kc. Okay. So this is how it concludes. And so now I only have to show this thing with the greatest common divisor. So we can see it. See? So we know that G over F, we have G is equal to x minus y1 times x minus yn, where these yi are different. Distinct. Particular. And we have that if we look at h of yj for j different from 1, this is what? This is f of c minus z times yj. And by the condition, I mean, how we had defined this z, this is not equal to any of the xi's. So this is different from xi for all I equals 1 to n. So these are precisely the zeros of f, so this is not 0. Okay. So we see that h does not vanish at any of the yj's different from b. On the other hand, so a greatest common divisor must divide G. So I can always choose it to be monic, so then it must have some zeros. One can see it here. So it follows it must be a product of some of these. So the greatest common divisor of H and G is a divisor of, in particular, the monic one, is a divisor of G equal to x minus y1 into x minus yn. So it must be a product sum of the x minus yj. But we can see if it's it cannot contain any of the x minus yj except for x minus y1, which is x minus b, because these are not zeros of h. Thus, x minus b is the greatest common divisor. Okay, so this is the proof. So it's rather tricky and a little bit long. So we have somehow, obviously I kind of gave it in a logical order, but somehow maybe when you, I don't know precisely where the proof comes from. You know, you have several ideas, you know, that you want to use this thing with the greatest common divisor, and then you somehow construct it from there backwards, that you make this trick that you want to find this polynomial h, which has only this one factor in common with it. And in order to do this, you need to find this z. So in some sense, I think the proof comes from the, you know, is constructed from the other end. Okay. So this was this using the one of the more difficult proofs. So now I don't have much time left. I can just briefly start explaining what I will explain on Wednesday. If I want to make a short interlude into finite fields, we somehow now know enough to, in some sense, give a complete classification of finite fields to isomorphism, so that we can precisely see what are the finite fields. So when I started to study myself, I thought that the finite fields would be just the fields with p elements for p a prime number, but that turns out not to be true. But on the other hand, you know, it's quite easy to see what all the finite fields are. So we want to classify finite fields up to isomorphism. Obviously, if the field is finite, it must have the characteristic a prime number, because if the characteristic is 0, then you have the whole of the integers contained in the field, and that would be you know, 1 or 1, 2, 3, and so all these are different, so these are already infinite. So if f is finite, then the characteristic of f is a prime number. E, and we know that ft equal to z mod pz is a field with p elements. So as a remark, let f be a finite field of characteristic p, then I can look just at the multiples of 1, you know, just adding 1 plus 1 plus 1 and so on. So the set of all n times 1 with n in Z is obviously contained in F, and you can easily see if this is of characteristic P, then this is isomorphic to Fp. No? So that means F contains a subfield which is isomorphic to Fp. Then we don't worry about isomorphism, so it contains Fp as a subfield. So that means F is a field extension of Fp. As F itself is finite, it follows that it's a finite field extension of Fp, because if it was an infinite extension, then it would have infinitely many elements. So F is a finite extension of Fp. And you know, in particular, it follows it's a finite dimensional vector space over Fp. So it means, you know, if the degree of the field extension is n, the number of elements is p to the n. Thus, if n is equal to the degree of f over fp, then the number of elements of f is p to the n. So we have now found out that the possibilities for the number of elements in the finite field are only the powers of a prime. Okay? And now, so now my time is up. I'll just say next time we will show there are up to isomorphism. So for any prime power, Q equal p to the n, there is up to isomorphism a unique field with Q elements. So for every prime power Q equal p to the n, there is a field with p elements, with p to the n elements, and any two such fields are isomorphic. Okay. Okay, maybe I will stop here because now get to the details. Okay, thank you.